Okay, this is Lab 5, Magnetic Braking with Faraday, and my name is Jonathan Paparo. The purpose of this lab is to collect data on a magnet flowing through an aluminum tube in order to observe and apply Faraday's law. The experimental time was 1.25 seconds, and the computational was 1.118 seconds. The physics principles used are Faraday's law, Biot-Savart law, Newton's second and third laws, Ohm's law, magnetic force on a loop, and time derivative of a magnetic flux of a dipole. These will all be used to either find a computational answer or to help conceptually with topics throughout the entire lab. So the magnet was used to model a magnetic dipole, while the aluminum foil modeled a tube through which it fell. The assumptions are that air resistance is negligible, it doesn't have any effect, and that pretty much means that gravity and magnetic force from the aluminum tube due to the induced current from the dipole are the only forces acting on the magnet. And that allows us to equate the magnetic force and the gravitational force equal to each other, because we know that in our velocity graph, the velocity versus time graph, when the slope is equal to 0, then the net force on the system is equal to 0. So you know that gravity and magnetic force have to balance out. So then you can find your magnetic force via that manner. And then the system is the aluminum tube, and the magnet surroundings are everything else. The procedure: first I use the magnetometer on my phone to determine the north pole of the magnet. Then I set my camera up to record and drop the magnet through the aluminum foil tube 5 times. Then I used my video footage to calculate how long the magnet took to fall through the tube in each trial. This is the data that I got using those procedures. Yeah, the average is 1.25 as shown on the introductory slide. The lab questions: why can't we use a ferrous tube, for example, or a steel pipe? The new tube would have magnetic properties that would interfere with the magnetic force already produced, so that just wouldn't really work. And then it would interfere, so it wouldn't work as well. And what happens to a magnet? How does this compare to a magnet falling in free space without a tube? So the magnet experiences an upward force from the induced current in the aluminum foil, creating a lower acceleration and lowering the average velocity through the tube, causing a longer fall. And then these are the computational models I use to achieve my number that I showed in the introduction, the 1.1 number. And yeah, this just models the gravitational force and the magnetic force upwards from the induced current. So that means that our computational model is what we should have gotten for our experimental, but the difference between them is other errors, such as us treating drag as 0. And yeah, here's the velocity versus time graph that I was talking about. So as you can see, when the slope is 0, acceleration is 0, so you can equate those two. And then more lab questions. The first question, I'm not going to read all that. By applying Lenz's law, you can deduce that red corresponds with counterclockwise and blue to clockwise. The combinations of these two slows the magnet down as it falls. The second question: it would still be slowed as it falls, but would change the current direction. So it'd be the same experiment, literally. If you dropped it, you should get the same times. And then for the third question, the times were relatively similar, as I discussed previously, and this could be due to errors such as human timing error or drag being actually present when we said it wasn't. And then the last question, as I've said before, it tells us that the forces are initially not balanced, but eventually F net's equal to 0, as I've said before, yeah, when the slope is equal to 0. Sources of error: air resistance actually is not negligible in the real world, and it could have a slight effect on the upward force. So yeah, that would make us slower, and that makes sense with the experimental to computational data. So that would be a fair point. And the conclusion questions: what if the resistivity? I don't have time to answer. going to say that. Resistance and current are inversely proportional, meaning the current's magnitude should increase. This would cause the magnetic force to increase as well, thus slowing the fall of the magnet. And then the second question, holes or slots would most likely cause less rings of current and thus decreasing the magnetic field and force, causing the magnet to fall faster. Just in time.